Alright, this is chapter 13, beginning with number 18. It says the vibration frequency is equal to 8.66 times 10 to the 13 hertz. Remember, a hertz in basic SI units is the inverse second. We want to know how long does it take the molecule to complete one oscillation. That's the period. The period is 1 over the frequency, which will give us units of seconds. And 1 over 8.66 times 10 to the 13 is 1.2 times 10 to the minus 14 seconds. It says write expressions for simple harmonic motion with amplitude 10 centimeters, frequency 5 hertz, and maximum displacement at t equals 0. And then in part B with amplitude 2.5 centimeters, angular frequency 5 radians per second, and maximum velocity at t equals 0. Alright, well, for part A, we want to write expressions x of t, that is the position as a function of time, is equal to the amplitude times the cosine of the angular frequency times time plus the phase difference, or the phase shift phi. So we want to create expressions. We want to know what A, omega, and phi are. A is the maximum amplitude. So in part A is given. It's just equal to 10 centimeters. That is, what is the maximum amplitude of the oscillating body, whatever it is. In this case, it's 10 centimeters. The frequency here is 5 hertz. Frequency is 5 hertz. But we want to know what is the angular frequency, that is, what is omega. And omega is equal to 2 pi times the frequency. Right, if you look at this, the units will give you radians, because 2 pi radians here times 1 over seconds, that gives you radians per second. So that gives you the angular frequency. 2 pi times 5, that gives you 10 pi. This is in radians per second. And then we also want to know what phi is. Well, we want to look at this. It says that the maximum displacement is at t equals 0. So if we were to draw x versus t, the maximum displacement would occur at t equals 0. Right, this is the maximum displacement at t equals 0. And this is a cosine function. You know, the cosine of 0 is equal to 1. So this is the proper representation of a cosine function. So we don't need to shift the wave function at all. So our phase shift is equal to 0. So if we write the function x of t is equal to a, which is 10 times the cosine of omega, which is 10 pi t plus 0, which of course is just 10 cosine 10 pi t. So that's part A. Now in part B, the amplitude is 2.5 centimeters. The angular frequency is 5 radians per second. So omega is 5. I'm going to write it as radians per second, but they just write it as 1 over seconds. It's the same, because radians isn't really a unit. And the maximum velocity is at t equals 0. So if I'm going to draw my position function x versus t, my maximum velocity occurs when the displacement is 0. That is, when the object, the oscillating object, let's say it's a mass on a spring, the maximum velocity occurs when that mass goes through the equilibrium position, and that's at x equals 0. So my function is going to look like this. Alright, at this point, at t equals 0, I have maximum velocity because it's passing through the equilibrium position. Further, I have positive velocity because the slope of this point on the graph is positive. Alright, now, in order to get this, I need to shift the curve to the right by a quarter wavelength. So the normal cosine function looks like this. If I take it over to the negative, alright, I want to shift so that this point comes right here. That is a shift of 1/4 of a wavelength. Alright, 1/4 of a wavelength. And in radians, that's equal to pi over 2. A full wavelength is 2 pi radians. So 1/4 of a wavelength is pi over 2. Now, in order to get a shift to the right, we need a negative phase difference. So a negative phi shifts the curve to the right, or the function to the right. Alright, so our phi then is negative pi over 2. Now, I said this is our position function. If I was to plot the velocity function versus time, which is just the derivative of the position function, it would look like this. Right? So I can write my displacement, that is my function for x for this. X of t is a, which is 2.5 cosine of omega, which is 5, times t minus pi over 2. So that is my displacement function for that. This is part A. The top of a skyscraper sways back and forth, completing 9 oscillation cycles in 1 minute. Find the period and frequency of the motion. Well, the period is just equal to the total time divided by 9. So 1 minute is for 9 oscillations. So if we divide that by 9, we get 0.111 minutes. And then we convert that to seconds. It's 6.7 seconds. So it takes 6.7 seconds to oscillate back and forth. And then the frequency is 1 over the period, which is 0.15 hertz. It says a 200 gram mass is attached to a spring of constant k equal 5.6 and set into oscillation with a equal 25 centimeters. We want to know what is the frequency, the period, the maximum velocity, and the maximum force in the spring. Okay, well first, we know that the angular frequency is equal to 2 pi times f. Now, specifically for a mass on a spring, omega is also equal to the square root of k over m. So this is a general statement, and this is a statement that's true for a mass on a spring. So in order to determine the frequency, I can set these two equal. I can say that 2 pi f is equal to the square root of k over m. And then from that I can calculate what is the frequency. So the frequency is 1 over 2 pi square root of k over m. That's 1 over 2 pi square root of 5.6 over m, which is 0.2 kilograms. And that gives me my frequency, which is 0.84 hertz. In part B, I want to know the period, simply 1 over the frequency, and that's 1 over 0.84 or 1.2 seconds. In part C, I want to know the maximum velocity. Now, we said that x is equal to a cosine of omega t, and so dx dt is equal to a omega sine of omega t. This was our maximum displacement. This is our maximum velocity. So our maximum velocity, Vmax, is equal to a times omega, which is equal to a. I set up here that omega is 2 pi times the frequency. So that is the amplitude of 0.25 meters, 2 pi times the frequency, which is 0.84 hertz. And that gives us our maximum velocity, which is 1.32 meters per second. And then finally in part D, if I carry this a step further, I want to know what d squared x dt squared, that is the derivative of this function, is going to be a omega squared cosine of omega t. Alright, so this is my maximum acceleration. The maximum acceleration is a omega squared. So the maximum force is equal to the mass times a omega squared, which is 0.2 kilograms, a, which is 0.25 meters, times omega squared, which is 2 pi, times the frequency, which is 0.84 squared, and that gives us our maximum force, which is 1.4 newtons. It says an astronaut is orbiting spacecraft is weighed by being strapped to a spring constant of k equal 400 newtons per meter and set in a simple harmonic motion. If the oscillation period is 2.5 seconds, what is the astronaut's mass? So our period is 2.5 seconds, and our k value, our spring constant, is 400 newtons per meter. We want to know what is his mass. Well, as I said before, omega is equal to 2 pi times f. That's a general statement, which is true. And for our spring, omega is also equal to k, the square root of k over m. So just as we did before, I can just set these two equal. 2 pi f is equal to the square root of k over m. And then I solve for m, which is k over 2 pi f squared, which is k over 2 pi 1 over the period squared. And I put in these numbers. K was 400 divided by 2 pi times 1 over the period, which is 2.5 squared, and that gives us a value of 63 kilograms. So the astronaut's mass is 63 kilograms. It says that the heart of a grandfather clock is a simple pendulum 1.45 meters long. The clock ticks each time the pendulum reaches its maximum displacement in either direction. What is the time interval between ticks? Well, as I said before, omega is equal to 2 pi f. It's a general statement. For a pendulum, omega is also equal to the square root of g over L, where g is the acceleration due to gravity and L is the length of the pendulum. So I can set these two equal to one another. 2 pi f is equal to the square root of g over L. This is 2 pi, frequency is 1 over period, is equal to the square root of g over L. I know what L is. L is equal to 1.45 meters. I know what g is, of course, it's 9.8 meters per second squared. And I want to know what is t. So t works out to be 2 pi square root of L over g. So t is 2.42 seconds. Now, on a pendulum, that 2.42 seconds occurs when it goes this direction and then back to the point where it originated. But it says here that the clock ticks each time the pendulum reaches its maximum displacement. So it clicks here and then it clicks here as well. So our time between ticks, I'm going to call it t ticks, is equal to the total period divided by 2, which is 1.21 seconds. Wheel rotates at a rate of 600 revolutions per minute. Viewed from the edge, a point on the wheel appears to undergo simple harmonic motion. What are the frequency and the angular frequency for this simple harmonic motion? Well, we're given omega, and that's equal to 600 revolutions per minute. Now this is the same omega that we're talking about when we talk about simple harmonic motion, because an object in circular motion exhibits simple harmonic motion. It's the same angular frequency that we've been dealing with, the same angular speed. So I'm going to go ahead and convert this to radians per second, as we do. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds, and that gives me 62.8 radians per second. And that is omega, so that's actually part B. That's omega, and so this is the answer for part B, the angular frequency. And then for part A, we also know that omega is equal to 2 pi f. So f, the frequency, is just omega over 2 pi, which is 62.8 over 2 pi, which is 10 hertz. Okay, it says a 1,400 kilogram car with 4 shock absorbers is bouncing up and down the highway at 20 meters per second. The amplitude of the oscillation is 18 centimeters. What is the total energy in the oscillations, and what fraction of the car's kinetic energy is this? So our energy in this simplified form, the total energy is equal to the translational energy plus the vibrational energy. the car is traveling forward, so it has a certain kinetic energy, a translational kinetic energy, but it's also bouncing up and down, so it also has vibrational energy. We've talked about these already. Translational energy is just 1/2 mv squared plus the vibrational energy, which is 1/2 kx squared. So since omega is equal to 2 pi f and omega is equal to the square root of k over m for a spring, I can say that the square root of k over 2 pi f is equal to the square root of k over m, and I can create an expression for k that's in terms of m and f. So if I solve this for k, I get that k is equal to m times 2 pi f squared. So I'm going to plug that in here so that it's an equation that I can solve. So 1/2 times the mass, which is 1400 kilograms, times the speed, which is 20 meters per second squared, plus 1/2 of k, which is m, 1400 kilograms. That's the mass of the car, times 2 pi, and the frequency is 0.67. That term is squared. So that is k, and then x is 0.18 meters. That's squared. That gives us the total energy. I'm just going to do it in separate terms. 2.8 times 10 to the 5th plus 402 joules. So the translational is 280,000. The vibrational is 402 joules. I'm going to write it out disregarding sig figs and just write it as 28,402 joules. Now if I want to know what percentage 402 is of the total, say 402 over 28,402 times 100 gives me 1.4%. So the total energy of the car is mainly kinetic, translational kinetic energy. 1.4% of it is in vibrational energy. Okay, a 450 gram mass on a spring is oscillating at 1.2 hertz. The total energy oscillation is 0.51 joules. What is its amplitude? Well, a similar problem is what we did before. I have E is equal to 1/2 mv squared plus 1/2 kx squared. That's the total energy, 0.51 joules. It's the energy in the spring plus the energy plus the kinetic energy. We're assuming that you have this spring that's set up like this, and so this object is oscillating back and forth. So there is no gravitational potential energy. Now, I want to know what is its amplitude. I'm going to make some substitutions here. I know that x is equal to a cosine of omega t. I also know that v, which is the derivative of x with respect to t, is a omega sine of omega t. Excuse me, it's the negative of this actually. So negative a omega sine omega t. So I can substitute these in for v and for x, and it works like this. I get E is equal to 1/2 times m times v, which is minus a omega sine of omega t. That is squared plus 1/2 k times a cosine omega t, which is also squared. That's x. And now if I reorganize this a little bit, I have 1/2 m omega squared a squared sine squared omega t plus 1/2 k a squared cosine of omega t squared. Since omega is equal to the square root of k over m, then I can say that k is equal to omega squared m. So I can rewrite this further and say 1/2 m omega squared becomes k a squared sine squared omega t plus 1/2 k a squared cosine squared of omega t. We have a common term here, 1/2 k a squared. Alright, this is a common trig identity. Sine squared plus cosine squared is equal to 1, so this simplifies to 1/2 k a squared. So our total energy is 1/2 k a squared. We want to know the amplitude. The amplitude then is equal to 2 the square root of 2e over k. The square root of 2e, as we've already said, k is omega squared m. Square root of 2e 2 pi f squared m. Now I have everything that I need, because F is 1.2 hertz, mass is 0.45 kilograms, and E is 0.51. So this is square root of 2 times 0.51 joules divided by 2 pi 1.2 hertz squared times m, which is 0.45 kilograms. And that gives us the amplitude, which turns out to be about 20 centimeters, 0.2 meters.